In our previous 670cc Predator-powered Renault video, we were able to tune the engine for maximum performance and maximum fuel economy. So more or less we ended that video with a win-win, but now we're back to try to unlock more performance from this little engine. Today we're going to fit an oversized motorcycle carburetor to this Harbor Freight engine and see if that helps or hurts performance. Now if you watched the previous episode, then you're probably aware that we plan on using a 32mm Keihin CVK carburetor plus a billet intake manifold from Performance 670. Now this combination of parts was never meant to be joined together, so it's going to take a bit of clever ingenuity to make this work. But before we get started, let's take a closer look at the carburetor we're replacing. So this is the stock carburetor that came with our 670cc Predator engine, and right away you can see that it's a 2-barrel carburetor. But not so fast. You see, this 2-barrel would normally be awesome, however it's actually 2 single-barrel carburetors in one housing. And what I mean by that is, each side of this carburetor feeds a single cylinder. Meh, all of a sudden this rather large carburetor just got a lot smaller. Now each side of this carburetor has a 28mm throttle plate, and internally it has a 22mm fixed venturi. The size of the venturis are important, and we'll dig into that deeper in a minute or so. Our new carburetor has a 32mm throttle, which is a nice upgrade from the 28mm throttle on the stock carburetor. And since this is a variable venturi carburetor, the venturi can also open up as much as 32mm. So with this carburetor at wide open throttle, well, we have a 32mm hole all the way through the carburetor with no restrictions from the venturi. Now, judging from some of the comments I got from the last carburetor episode, I think some of you folks are missing the point on this carburetor experiment. Alright, so let's do a quick carburetor 101 lesson. So here's a simplified drawing of a carburetor cross-section. Over here we have the air going in, we have the venturi, we have the throttle, and we have the air-fuel mixture going out. So let's focus on the air entering the carburetor. Well, everything's fine until it comes across this bottleneck, and actually this bottleneck is called the venturi. Once the air reaches the venturi, well, the velocity of the air will actually speed up, and that helps draw in the fuel from the float chamber into the carburetor. And this is where the air mixes with the fuel. This is overly simplified, but hopefully you get the point. Anyway, let's say the carburetor is 28mm in diameter and the venturi is 22mm. Well, right away we can see the 28mm diameter is severely restricted by the 22mm venturi. And that's both good and bad. You see, the good news is the smaller venturi does an excellent job atomizing the fuel, and the throttle response is going to be awesome. The bad news is the small venturi will suffocate the engine at high RPM, and the engine isn't going to make much power there. So the logical thing to do is get a bigger carburetor. And through the magic of editing, now we have a bigger carburetor, which will have no problem feeding the engine all the air it wants. The bad news is the size of the venturi is also bigger, and that translates to a slower velocity of air going through the venturi at low RPM. The new problem is, with this large venturi, the fuel isn't going to atomize very well, and the throttle response is going to suffer. Overall, the engine will likely run like crap at low speeds, but once the engine reaches higher RPMs, well, the bigger carburetor will start working better because the overall velocity of the air going through will be much greater and will allow the fuel to atomize properly. So the big carburetor will help make power on the top end, but performance on the low end will suffer. And the little carburetor will give great performance on the low end, however the performance on the top end will suffer. Now a quick side note. This is why we can't use a conventional automotive carburetor on this engine. The venturis on an automotive carburetor are way too big for this small displacement engine. So nope, no automotive carburetors on this project. They just won't work on this Predator engine. So what we want is a big carburetor with both a small and large venturi. Well, they don't actually make such a carburetor for a small displacement lawnmower engine, but they do make something like that for a motorcycle engine, and that's this variable venturi carburetor. Now, this Keihin CVK carburetor that we're using has a throttle butterfly and an infinitely variable venturi. So you can see with my crappy animation, the venturi size of this carburetor can be tiny at idle and huge at wide open throttle. And this will basically allow us to use an oversized carburetor on a small engine with theoretically good performance on both the top end and the bottom end. Now all we need to do is make it fit our engine. So this Keihin carburetor is never used for upgrades on the 670 Predator engine. You see, the simple upgrade is to use a large bore Mikuni flat side carburetor, But that's not what we're going to do. We want the automatic variable venturi that's found in the Keihin CVK carburetor. And that's kind of a problem because you can get a billet manifold for Mikuni flat side, but unfortunately, there's just no easy way to make a Keihin carburetor fit that manifold. Yeah, I know it looks like it should be easy, but it ain't. So obviously this is the manifold, and off camera we drilled and tapped the manifold for the rubber flange that mounts the Keihin carburetor. Meh, this is a straightforward modification and nothing special about it. Until you realize that this hole interferes with one of the manifold mounting bolts. Then the bad words start flying, but we have a solution. So this is one of the long bolts that came with the manifold, and it interferes with the bolt for the flange. You see, both bolts want to occupy the same space at the same time. So our solution was to counterbore the manifold to allow a shorter bolt to be used to secure the manifold to the 670 engine, and that allowed us to cross-drill the manifold so we could use a slightly longer bolt to fasten the flange to the manifold. The end result is both bolts can do their job as expected, and we can move forward with the installation. The fuel pump that came with this Predator engine is a pulse type, and we've had nothing but problems with it from day one. If the car sits for a few days, well, the fuel pump will lose its prime, and then it's extremely difficult to get the engine running again. Anyway, since we needed to relocate the fuel pump to mount the intake manifold, we decided to relocate the fuel pump to the trash can and try something different. So in order to supply fuel to the new carburetor, we're going to use a $10 electric fuel pump that's available on the Jungle site. This pump actually puts out too much fuel pressure for the simple carburetor, so we went ahead and got a deadhead type fuel pressure regulator. Now I've heard a lot of folks had problems with these regulators in the deadhead configuration, so we went ahead and added a return line, and long story short, here's a cartoon of what we built. Now I'm sure it may defy logic, but future Jimbo says it works fine. Yeah, it works fine, no worries. Anyway, that's what we did to solve the fuel pump and fuel pressure issue. So with most of the initial problems solved, let's go ahead and assemble the induction system and see if we can find more problems. So the first thing, of course, is the manifold, and since we've modified it, this guy shouldn't give us any problems. Next is the carburetor flange, and this should also fit perfectly on the manifold. And now the carburetor. Now we have to go back and modify the jets on the carb, but first we need to get the engine running to figure out what direction to go in. This carburetor uses an enrichment device instead of a conventional choke. Meh, it's common on motorcycle carburetors. And now the throttle cable. So off camera we spent a lot of time modifying the throttle linkage over here to get the throttle to move correctly. Initially, the throttle would only open a quarter of the way when the accelerator was floored. Now with the modified linkage, we're able to get wide open throttle on this carburetor. So with everything assembled, we noticed the carburetor wasn't supported very well, and it was putting a lot of pressure on the intake flange. So once again, off camera, we fabricated a brace to support the carburetor. Normally on a motorcycle engine, the airbox is what supports the carb, and in the absence of a proper airbox, we elected to build a mini bridge under the carburetor. So now we're ready to start the engine. And fast forward a bit and the engine's running. It's running a little bit lean, and it looks like we're going to have to change the main jet. Alright, now it's time to figure out what jets this carburetor needs. Over here, this is the pilot jet, and this is the main jet. Now, the pilot jet is responsible for the mixture at idle, and as far as the idle goes, this jet seems fine. Now, the main jet is responsible for the mixture once the throttle is open past the idle area. So, when you open the throttle, well, it's the main jet that takes over and provides the fuel for acceleration and cruise. Now, keep in mind, the pilot jet doesn't just stop working, it also provides a tiny bit of fuel once the throttle's opened. But for now, we're going to focus on the main jet, and to correct the lean condition, this jet needs to be bigger. Well, we went through our box of standard sized jets, and the biggest one we have still causes the engine to run lean, so we're going to have to drill out a jet for a size bigger than standard. Fast forward a bit and we're ready to take the car out for a test ride. Now keep in mind we're using a wideband gauge to tune this carburetor, and well, things aren't looking good. Let's take a look. So this simple chart I made is not to scale, and it's just to help visualize what's going on. Now at idle, we're getting an air-fuel ratio of about 12.5 to 1, which is perfect for this air-cooled engine. Now at part throttle, the air-fuel ratio drops down to 9.5 to 1, which is a bit on the rich side. Now this is at part throttle, so when driving the car around town, we're seeing this air-fuel ratio. and that's not good, but the engine seems to run great. Once the car starts to speed up, then the air-fuel ratio starts leaning out, and it goes very lean. So anyway, even though the air-fuel ratio is all over the place, the engine runs fantastic. Now, if I didn't have the wideband gauge available to watch the air-fuel ratio, I would swear the car is running perfectly. It literally is running that good. Obviously, I need to continue experimenting with the jets, but before we go any further, I want to take the car out for a performance and fuel economy test. You know, just to get an idea on how the car performs with what feels like a good tune, but in actuality, this is far from perfect. So around town, the engine's running pig rich, but it feels fine from the driver's seat. It's incredible how well this engine runs with a half-finished tune. Once we hit the open road and the car got up to speed, it's now running too lean. But once again, you would never know it from the driver's seat. If I didn't have the wideband gauge to look at, I would presume everything was fine. Now, due to the extreme temperatures during the day, we've taken to driving this car in the evening where the lighting is better and the temperatures are a little bit lower. Well, after taking the car out for a 30-mile trip to nowhere, we measured the fuel economy and the car got exactly 41 miles to the gallon, which ain't half bad, but as I recall, the previous fuel economy test yielded about 44.5 miles to the gallon. So running on the lean side didn't help with the fuel economy at all. Alright, well, let's take the car out for a performance test and see how it does. Okay, so today we're going to do a 0 to 55 mile per hour acceleration test. This time around, I'll be holding the wideband gauge so you folks can get a better view of how off the air-fuel ratio is. The time to beat is 31.03 seconds. Oh yeah, for the new viewers, this car has both a CVT and a 4-speed manual transmission. For this test, as well as all the previous tests, we'll be starting off in 3rd gear. Believe it or not, this is the best gear for getting up to 55 miles per hour in a hurry. The engine's running great, but I can definitely tell it's not making any power with the air-fuel ratio as high as it is. Wow, what a huge difference. We were a little over 9 seconds slower, and for the most part, the engine runs fantastic. Well, almost. At the tail end of that acceleration run, I could definitely tell it was running lean just from the feel, and of course the wideband gauge confirmed that to be true. Now, this wasn't a pointless test. It kind of shows that to tune this carburetor properly, we really do need a wideband gauge. So this dip in the air-fuel ratio at part throttle concerns me, and modifying the main jet to correct this portion of the chart will only make this dip bigger. Now, I'm no expert on these carburetors, but I think the trouble's not in the jets, but may in fact be in the emulsion tube. And on this carburetor, the emulsion tube is located here. Now, this is the only tube I have at the moment, but I do have some more on the way. So unfortunately, this project will have to go on hold for a day or so until the new parts arrive. The good news is, we were able to solve a lot of other issues, and believe me, there were a lot in order to get this carburetor to fit the engine, and to make the fuel pump work and the throttle work. I hate to end the video like this, but it's Friday evening once again, and it's time to wrap the video up so I can upload it tomorrow evening. Anyway, I had fun getting all these parts to work, and I learned a thing or two. Hopefully you did as well. Until next time.